So today we'll start talking about open channel flows. Not so relevant for many of the majors in this, but kind of rounds out the material. So 10 and 11, weeks 10 and 11 were pipe flows. Weeks 12 were unbounded flows. What did we call them? Flows around objects. And this 13 will be our last week, and we'll talk about open channel flows. So, the Penn State always used to have a very active whitewater boating club. When I came here a long time ago, certainly in the early 90s, I guess now 30 years ago, I used to go whitewater boating, not up to this standard, but they still keep a slalom course in Bellefonte, just downstream of the big spring. So the big spring is a big spring which runs pretty much the same rate all year round, and so most of the streams around here are ephemeral streams which dry up or at least get low in the summertime. But the big spring, which comes up in Bellefonte, you drive past it on the way into the traffic light in Bellefonte, pretty much runs, I presume, at the same rate year round, and it certainly keeps that part of Spring Creek just below Bellefonte and above Milesburg at pretty much the same level. There's always water in it, and so there are a bunch of gates put in it to run competitions. They have a Pennsylvania Cup, one of which is down in southeastern Pennsylvania, Yorkish. It has about 5 or 6 different streams. One of them actually might be Loyalsock as well. There used to be a Loyalsock race as part of this series. And the Pennsylvania one runs in sometime in October. I think it probably still runs, but Penn State decided they were a little nervous about the risk management of all these things, and they wanted to organize the outing club in a different way. So it used to be kind of half townspeople and half university folk, and they basically shut it off to the townspeople. So it was a nice arrangement because the townspeople kind of gave it continuity. They had cars, students don't necessarily. There was an active instruction program. You could sign up for 6-week hard shell kayaking course on Spring Creek, and the boats were kept at the natatorium in downstairs. There used to be a February pool slalom, which involved stringing gates across one of the indoor pools at the Nat, and including an Eskimo roll as part of the circuit. And so it's open channel flows today, and so this is reminiscent of this. And I guess we talked about this either on the first time or second time we met, and the idea is that just like skiing, going downhill, you're using gravity to pull you downhill, and acting against you are two forces. I guess there's friction on the bottom of your skis or your snowboard, and there's also air resistance pushing you back up the hill, so to speak. And so the speed you go at is the balance between the potential that you're losing in going downhill, balanced against the friction, both of the snow and the air going around you. And so surfing West Virginia is pretty much the same as that. It's a bit more obvious if we go to one of the different, this particular one here. I don't know if this will, not this one, but this one is if you're surfing a wave. It's the same as surfing a wave. Hey there. And if you're on the face of a wave, the water's coming downstream past you. I want to run it again if I can get there. Oh, geez. I don't know how to do it. Well, so you can imagine it. So you're sitting on the surface of a wave. You're pointing down the wave. The wave is flowing past you. It's the same as the friction on the bottom of the boat as if you're skiing. And your weight vector is directed down the face of the wave. And so those are the two forces that are balancing each other. The water in this case is moving instead of a static mountain that you're snowboarding down. And providing that force against you. I guess if you're not moving physically relative to space, then there's no air resistance as there is for skiing. But those are the forces that are balancing. And so, as I say, not so relevant for the things that we do in the majors in our 4 programs that are represented here: mining, petroleum, energy, and environmental systems engineering in terms of open channel flow. Certainly external flows in week 12 and pipe flows are by far the most relevant to what we do, both for pipes as in drill holes and also as in porous media capillaries, representing that. So anyway, so that's where we are. I can't see my cursor. And so the final one to show is, I guess it's standing wave, is hydraulic jump. And so the other thing that makes it kind of interesting for us and different from the other things we've done is that maybe for external flows it's a little bit the same, but if you think about this flow regime as flow in a pipe, then if you drew a weir upstream and downstream, then by definition, since we're not accumulating fluid in the middle, then the flow rates, the product of cross-sectional area times velocity, have to be equivalent, our continuity requirement. And so here, upstream, we have a small cross-section of flow, but a very fast flow. And downstream, we have a much bigger cross-sectional area. And so by definition, if we have the same volumetric flow rate, we have a much slower flow. And so seemingly, the flow can either organize itself so it's going very quickly in a small section or very slowly in a large section. And so how do we work out what the mode is by which it chooses between those two different modalities? It's different from pipe flow, because pipe flow, you're constrained to being flowing within the section of the pipe and filling the pipe. Of course, if you have pipe flow that's only half full, then it's really not pipe flow at all, it's open channel flow, as we'll talk about in this a little later. So that's kind of the view of what we'll deal with in this class for this last week, which we are together for. So I'll go to this, and I'll go to this. I guess I have to get used to doing this again. Oh, I didn't want to do that. Okay, yeah, I thought it was me. Greetings. So made the case that we're talking about open channel flows. We've talked about flow classifications. So we made the case that it can either flow very placidly, like the rivers we're used to around here, where the section really doesn't change, cross-section area flow doesn't change very much as we go downstream, or it can go in these so-called gradually varying or rapidly varying flows that we just saw for the hydraulic jump. So we'll talk a little about flow classifications. We'll define hydraulic radius to supplement what we already know about hydraulic diameter. And then today we'll really only talk about uniform flows. So uniform flows are the kinds of flows that we get if there's no difference in the cross-section between upstream and downstream. And then we'll move on to talk about more complicated cases. We won't talk about that today. We'll talk about flows where the cross-section, cross-section does vary between upstream and downstream. I was sitting on my own at 7:45 before the first couple of guys turned up. So thanks for coming out as we roll these things up again. And so we probably won't talk about gradually varying flows at all. And so the essence of what we'll deal with is open channel flows. And so as we've done with lots of things, it's probably useful to recap, and I think it is specifically for this last of our three topics. And so that's what I plan to do first. So we'll put this in the context of everything that we've talked about so far in terms of practical matters. So we talked about fluid properties. We talked about fluid statics at a point and pressures on structures through week 3. 4 and 5 were Bernoulli, where there's no frictional losses in the systems. And then we talked about 3 forms of conservation. Conservation of mass, conservation of momentum, and conservation of energy. So conservation of momentum was just F equals ma, and Bernoulli defined in a generic sense. And then conservation of energy is when we have frictional losses in the system that we have to account for. And then the pragmatic part of our class was weeks 10 and 11, losses in pipes, week 12, losses in external flows, and now losses in open channel flows. So putting those three things into some kind of framework so you can see exactly what's going on is, if we talk about them in turn, we had these, we had pipe flow with some velocity between upstream and downstream. If the section stays the same, then those velocities are the same. And the whole characterization of that behavior, which you know well because I think you had it on one of your tests, is that we have this so-called Moody chart, which varies between the different regimes. And you know this. You can even tell me what the axes are of this. That this is friction factor, which is drag. We know that in this particular configuration that possibly we'd have something that looks like P1 minus P2 over gamma plus HP is equal to the sum of friction factor, length over diameter, plus whatever the flow velocity is. And we can divine it between these, and I'll try and do it on a common framework, is that the Reynolds number controls the flow. We have this break-even point around 2000. The Reynolds number is defined in terms of a diameter or a hydraulic diameter and a viscosity. These values are for roughnesses of the pipes. So epsilon is just this height here. And diameter is obviously the diameter of the pipe. You know all this. And that we have these two regimes, laminar and turbulent. And you know physically what they are. We know if it's a circular pipe, it's the friction factor is 64 over Reynolds number. And we know here that the velocity is proportional to 1 over the viscosity. And I guess here the velocity is proportional to the roughness, but it's not proportional to the viscosity in any way. It's really the density that's controlling this, right? It's not the viscosity in this particular case. And so we know how to be able to use this to be able to get solutions in a pipe. If we look at external flows, we could look at exactly the same geometry. I'll draw it again, but it could be a blunt-ended pipe in this particular case, right? So it's not flow through the pipe. And I suppose the difference is that we're interested more, we're interested more in for pipe flow, we're interested in the force exerted by the pipe on the fluid flow in controlling its velocity. And on external flows, we're more interested in the influence of the flow velocity, say on, shouldn't use this, but I will use it. This is uppercase D for drag, a drag force, right? And we know that we have a similar geometry. Actually, I could copy it from up below, but let's draw it separately. It looks exactly the same. I suppose the figures that we've looked at would look something like and we've talked about why this is for a sphere. This is coefficient of drag is equal to, I think, 24 over Reynolds number. So you see a direct comparison with this. We know that we can calculate the fact that the coefficient of drag or the coefficient of lift, they're just in different orientations, is equal to this squiggly d, a drag force divided by a half rho v squared times area. This is the kind of cross-sectional area that the fluid sees as it hits this. And again, the same behavior. This is something like 2000 of that order. This is Reynolds number. Yeah, again, this is turbulent. And again, you see that the coefficient of drag here is proportional to viscosity. It changes with Reynolds number. Or 1 over viscosity, it doesn't really matter if it's proportional to. And I guess the Reynolds number again is defined in terms of a velocity, a density, a characteristic dimension, and again the viscosity of the flowing fluid. And again, this is 2000. Yeah, and again, I guess this is written in terms of a change in pressure over a unit weight is equal to the squiggly d over a, which is a force divided by area. So this is a stress, which is multiplied by 1 over gamma. You can think of it in these terms. The pressure drop between the upstream face and the downstream face divided through by something has to be the same as equivalent to the drag force multiplied by the cross-sectional area. You can do a guillotine through this as a free body and look at the forces pushing this through making it stay static by the fluid impinging on it. It's the same as the truck at San Francisco Airport being blown off the tarmac by the 747. The force applied on here has to be balanced by this force that's being applied to the structure. So that's the definition of drag. And so the final one, so if this is pipe flow, or I guess we could call it internal flows, this is external flows. So internal, I suppose. Then the final one is open channels. Which is finally what we're going to talk about today. And all I really wanted to do is put it into the same context. And I suppose I should use the same colors. So the same context is that the channel would look like this. Oh, he's an artist, an artiste. And the essence of one of the things we talked about is that all of a sudden we get to choose, the water gets to choose what the cross-section would be. And I suppose this could be a velocity, or it could be a volumetric flow rate, which is just equal to the average velocity times the area. And the story continues because we have something that looks like this. And so this is all one and the same. It's something which is a Reynolds number, which is equal to a velocity, a density of the fluid, a hydraulic radius, typically defines it for just out of convention. You can do, I think, a hydraulic diameter is equal to 4 times hydraulic radius. Surprisingly, not 2, just the way it works out. And you have some graph that looks like this. And this would be roughness. Of the channel. And so whether the channel's concrete lined or grass lined or ditch or soil, uneven soil. And then this would be something what we'd call Manning's coefficient. Which we'll call lowercase n. And just to extend this, this is now 500, and it's 500 because it's a quarter of 1,000, just by the way that we characterize things. So it really would be 2,000 if we did it in terms of the diameter, but we do it in terms of the hydraulic radius. And this again is turbulent, and this is laminar. And it turns out that because the dimensions of these channels are so large, pipe, centimeters, an inch, of that order, channels, the Allegheny River, half a mile wide, perhaps not half a mile, but a quarter of a mile wide. Some of these, even the California aqueduct, these cross sections are large compared to pipes. And so almost always you're in this regime here. And so the expressions that work out for open channel flows are always in the turbulent regime, and they're always characterized by this behavior. And again, the Manning's coefficient is not proportional to viscosity, right? I guess. It doesn't change with viscosity, given by the fact that this relationship, if we drew it out, is horizontal. So the Manning's coefficients are just numbers that we'll see later, are 0.01 for a concrete line channel, 0.001 for glass line channel, etc., if such a thing exists. And so that's what we'll talk about today. So that puts it all in context, perhaps, of what we've seen for the last 3 weeks, weeks 10 and 11 for internal flows, week 12 for external flows, and now final open channel flows. And so that's what we'll talk about today. I'm just going to use the notes which I have rather than scribbling too much down. Of course, open channel flow can be kind of a pipe flow, but the main difference is if you have stuff going down a pipe and it doesn't fill the whole section, then it really is an open channel flow, even though it's not open to the external world, but a culvert would be open to the pressure. So the idea is that the pressure from upstream and the pressure from downstream short circuits in the air because it's such an easy conductor. So the pressure you have in the fluid can't be built up above a free surface, zero pressure at the atmospheric pressure at the surface, and then linearly varying with depth, where this would be P is equal to H gamma, right? As you go down. It would be the normal expression for a static fluid. And so even if it's in a pipe, then what the essence of open channel flows is that it's not being driven by a fluid pressure from upstream to downstream, but the only force that's driving flow is gravity. And so the only thing that matters is really what the gravity force is, and it's going to be the inclination of the pipe. So when we looked at the people surfing West Virginia, they're sitting on a face of a wave. The wave's going up underneath it. There's drag on the bottom of the kayak, on the boat, and there's their gravitational vector moving down, and the two are in exact balance. And so it's the same as ocean surfing as well. You're moving down the wave's kind of moving up underneath you, so it looks like you sit in the same portion on the wave as it moves as it moves into shore, I guess, and carries you with it. And so there are two dimensionless numbers which are important to us. One we know quite well. It's velocity, could be a diameter, and a density, and a viscosity. But the other one we haven't said much about is the Froude number. We know that the Reynolds number is the ratio of inertial to viscous forces. And this one we've seen before because we know that the celerity wave speed is equal to square root of gravity times the depth of the flow square root. We talked about this again in our first week here. And so surprisingly, if we know the depth of the ocean and we know what planet we're on, we can always calculate the speed, the wave speed, the natural wave speed of a tsunami or any other wave. And we can find out that it's quite fast. And this is part of the fact that clearly the only forces driving a wave are gravity and the inertia of the fluid not wanting to be moved at some new velocity. So the corollary for Reynolds number is Froude number for gravity-driven flows. And instead of driving through by the effects of viscosity, it's divided through by gravitational effects. Now, so we don't need to deal with this now, but the relevance of the Froude number is if you look at how fast a ship goes out to sea, it's how big the bow wave is. If you can minimize the size of the bow wave, because the bow wave is like being in a snowplow, stacking a whole bunch of liquid up in front of the bow of the boat, which then has to be pushed forward at a certain velocity. And since it's new liquid every time it's being pushed, it's not just the same liquid going at constant velocity, you have to accelerate it against inertia. And so the Froude number is due to that. We've made the case already that the number that controls the flow regime, so I guess the other thing that we could look at here is what makes these things different is that if this is a sphere that's traveling through the air, then what's different between these two regimes, I'm getting very skillful at this, is that, he says, famous last words, I don't know why it looks like that, is that the Reynolds number takes care of this creeping flow regime where it hugs the system, and when it's turbulent, then we get this vortex street forming at the back. So no longer does it hug it. And so this is the same, I guess you can think of it as viscous flows. If you blew this up, this would be a drag force applied to the side of this thing by the viscosity. And this is much closer to the truck on the apron at San Francisco, where it's getting hit by a whole bunch of velocity from the jet engine. It's hitting it at some velocity. You're killing that velocity by the stagnation at this front part. And the force that's applied from this is by killing the velocity of the fluid with some density, which is why it doesn't vary so much with viscosity, why this line is flat. And here, the force that's applied here is due to viscosity. And so that's the reason for the two regimes. So the same applies for this. I guess we're just making the same case, that for pipe flow, and I guess for external flows as well, was this, we've always said it's 2000 for laminar flow, a transitional flow between 2000 and 4000, and then turbulent flow beyond this. If instead of using diameter, we used hydraulic radius as our index, then it turns out being a factor of 4 or less, and it just follows through. But the same kind of ideas. And so I made the point already, and this is just, I guess, making the point further, that we're almost always in this regime to the right side of the laminar turbulent transition. It's not a sharp transition. We've said before that there's some kind of area in here, which I guess would be this 4,000-ish. It's pretty small because this is always a log figure for us, right? In terms of log linear figure. And that if we do the calculation for the Reynolds number for this, if you take a velocity, I don't know, I guess this must be 2 feet per second. I guess it is. This is in terms of slugs per cubic foot. I'm not sure exactly why I'm doing that. I guess we could do it in SI units. Why not? 2 feet a second is 1 meter a second. Hydraulic radius is going to be, in this particular case, the area divided by the perimeter. 10 feet is equal to 3 meters. 1 foot, well, let's make it 1 meter. Just because it's not 1 foot, but makes it easier. So if that's the case, then the hydraulic radius is equal to the area, which is 3 by 1, over the perimeter, which is going to be 1 by 3 by 3. Summed up, not the product. So 1 plus 1 plus 3 should be 5. So 5 divided by 3. which is about a half. That was 3 over 5. So velocity, hydraulic radius, density is 1,000 kilograms cubic meter. And if it's water, then we all know these numbers. And so that should come out to be, this is 10 to the minus 3, which is 10 to the 3. This is 3 over 5 times 10 to the 3. Yeah. So, well, I said it should be 3 over 6. Sorry. Someone should correct me, right? So it's huge. It's 10 to the 6, so 3 and 3. So it's a big number, so it's clearly much larger than 2,000. And in this case, it only has to be 500 is the threshold. And so for a very modest flow rate, but for a very wide section, then it comes out to be almost always turbulent. So the behaviors that we have in terms of the flows are classified in terms of these classifications. So the one we'll talk about today is uniform flows. So gradually varying flows and rapidly varying flows. So that's the shorthand that we'll use. And so when we're looking at flow within a channel, within a ditch, we're talking about the main aspect of it is that the upstream cross-section and the downstream cross-section are the same, as opposed to, say, for gradually varying flows where the upstream and the downstream are not the same. And for rapidly varying flows was our first case. If you're here early enough, we looked at a hydraulic jump. And so the water chooses to go at some high speed, but over a small cross-sectional area. And then for some reason downstream, it decides to go much slower, but over a much larger cross-sectional area, because it satisfies continuity that the volumetric flow crossing each of these gates is the same. There's no accumulation. And so we have to figure out exactly why the water decides to be in those two different configurations and what the reason for that is. So that's kind of the challenge that we have. We'll only talk about steady state flows. So in other words, if we look at this picture of these flows now or in 10 minutes, the water levels and the profile from upstream to downstream would be exactly the same, even though for a piece of water coming out of here, you would be seeing these different velocities as it goes downstream. Lots of non-steady cases we could deal with, but we won't. And then the essence of what we'll talk about today is only this one first case of uniform flows. And so for uniform flows, by definition, this depth of flow upstream and the depth of flow downstream is constant. If that's the case and its continuity is enforced, we know that v squared over 2g at each of these locations upstream and downstream are the same. We've talked in terms of the energy grade line and the hydraulic grade line before. Hydraulic grade line is just the pressure. This you can think of this as the pressure head, and this would be the elevation head, I guess, if you wanted to think about it in this way. So if this was Bernoulli, this would be upstream and downstream elevation. This would be the upstream. Y is equal to P over gamma, right? That would be this pressure here, would be equal to this height, etc. And the velocity head is the amount above this. And so for our uniform flow, upstream and downstream depths the same. By definition, upstream and downstream velocities have to be the same. And we can define the slope of the bed as being parallel to this hydraulic grade line. That's the deal here. And so the whole mathematical basis of this is that for uniform flows, the depth of water as it goes downstream doesn't change. That's all this is saying, is that the slope of the surface, this slope here, and this slope here are identical to each other. And so the idea is that we can define a simplified form of our system. So this is what the real flow would look like. It's a channel that has flow within it, just like a pipe. If you look at pipe flow, and we looked at this section vertically, I suppose, it would look something like this. Zero velocities at the boundaries and a maximum velocity in the middle. So if this was our plan view in looking down on this channel and taking a section across it, well, I guess you have it here, it would be fastest velocity would be in the center somewhere. Clearly, since it has a bed and a free surface, then the bed will also have maybe a zero velocity if it was laminar. But I guess actually you could think about it, since this isn't laminar flow, then there's a boundary layer here. So it's probably a small finite velocity at these walls, but certainly it's a lower velocity than in the center. And the maximum velocity is at this point here. And so what we're going to do is, rather than deal with this as a reality, we'll think of this as being an equivalent uniform velocity. And so we'll think about it as, I suppose we've called it V bar in the past. And so this is the velocity that we'd like to idealize it about, instead of this velocity V. And so with that, we can go through some relatively straightforward analysis. Don't know that we have to spend too much time on this, but it's nothing you haven't seen before. Momentum balance is F equals ma. We can also write it as mass times rate of change of velocity with time or space, which is equal to and so the reason for doing that is that the mass rate of flow, this is actually m dot v, right? This we know that the sum of the forces acting on the system is equal to the sum of the mass flow rates times the velocity. That's just momentum balance. So here, if we write the forces acting on the system, this here, density times volumetric flow rate, this term is just what we've called m dot. The velocity between upstream and downstream, if it's velocity 1 and velocity 2 are the same, then this term goes to 0 collectively, and sum of forces equal to 0. So we can take this as a free body, if we like, and we can look at the forces that are acting on it. The forces upstream and downstream, well, what do we say about the forces? We haven't proven it, but take it on trust. I'll use a different color. The forces should look something like this, if you can cast your mind back to what we said about pressures on structures. Probably making it more complicated than it needs to be. If the depths of flow are the same upstream and downstream, then the forces acting upstream and downstream, which are shown here, which come from these triangular distributions, have to balance each other. So this has to be the case here. And what are the other forces that we have acting down on this isolated block that we have? There's only two. There's a shear force that's acting on the bottom of this, which is shown here. And the shear force times the perimeter times the length is just, these two terms are the area. Right? The length is from upstream to downstream, so this is the length. The perimeter would be the channel. Let's see if I can do it. This length here would be the perimeter. And so the area would be the perspective of that established along it. So this has to be a shear stress acting on the bottom multiplied by an area. So this has to be a force. And the only thing that's driving flow is the vector of this weight, which is inclined relative to this line by some magnitude, which is W sine theta. the inclination. Theta is the inclination of the bed. So this is the force balance equation which we have to satisfy, which is obviously satisfying momentum balance because there is no change in momentum in the system. So if we write this out in terms of this parameter here, we can rearrange this term here. And if we substitute the value of sine theta as being equal to S0, which is approximately equal to sine theta for very small theta. So S theta is just going to be equal to, if you want to think about it, this is L and this is dz. So S theta is equal to dz over L. L could be the inclined distance, or it could be the horizontal distance. Because this is so small, they're both essentially the same. And so this is a very small number. S0 is a small number, but it's equal to substituting for this sign. So all we've done is get this term here instead of sine theta. We need to know the magnitude of the weight. So the weight is going to be equal to the area. Actually, why don't I do that in terms of fuchsia? Just going to get fancy here. Area. And this is the length, right? I've drawn this in the wrong orientation. A is obviously downstream, and this length here is looking upstream. But you get the picture. The weight is going to be the area times the length times the unit weight. Area times length times unit weight. Which we can put in here. The hydraulic radius is equal to the area of the perimeter. So if we substitute this here into this, we'll end up with unit weight. So this is, you end up with this. You end up crossing out the values of the lengths, which are on the upper numerator and denominator. We have an area and a perimeter, which by definition, that's why we use it, is equal to the hydraulic radius. And we end up with an expression, which is a straightforward expression. So we have the shear stress that's applied on the bottom of this bed is equal to the hydraulic radius, unit weight, and the gradient. So it kind of makes sense. Unit weight and gravity is, or unit weight is density times gravity, which is driving the flow because it's a gravitational flow. And a steeper bed means it goes, has a higher shear stress as you incline the bed more. And we never spent much time with this idea, but we certainly talked about things like in Bernoulli and the energy equation, HL is equal to KL V squared over 2G, right? You remember that? Head losses could be equal to a friction factor times length over diameter times V squared over 2G. For a pipe and for a fitting, they would be just in terms of a velocity through the fitting and a head loss in terms of a coefficient. Coefficient has no units because this is units of length and this is units of length. It's a head loss. And so this expression is basically the same expression as that. It's saying the amount of loss written as a stress instead of a head loss is given by a loss coefficient, velocity squared term, and the density instead of being on the bottom is or 2G on the bottom is this. And so what we can do is we could rearrange this expression here in terms of velocity. We already know what the value of this is. I guess it's this term here, right? We could substitute this term in here. And if we do that and we solve for by square rooting for the velocity, we end up with these terms. And the only important thing is this boxed equation in red at the bottom. But it basically comes out that these coefficients would be a loss coefficient, density of the fluid, and unit weight, which would include density and gravity in here. So this is a constant, and this is depending on the particular channel geometry, how steeply it dips and what its cross-section looks like. And so we can think of this as a coefficient, so-called a Chezy coefficient, French for the guy who, I guess it was a guy in those days, who developed it, multiplied by the characteristics of the channel. And you can sort out the magnitudes of this term, and we won't use the Chezy coefficient, but we'll use, which is, you can do a dimensional analysis, and in SI units, the value of this is going to be equal to the hydraulic radius to the power 1/6, divided by the so-called Manning's coefficient, which we haven't talked about. So you can use the so-called Chezy formula, or you can use the Manning formula. And Manning is much easier for us to use because you don't have to do some kind of conversion for a Chezy coefficient to get it. And all it says is that the velocity of flow in our system, and I suppose this would be kind of our average velocity, so it would be the blue one that we drew up here. So the average velocity, which would be kind of this across our system, is equivalent to a coefficient which for SI is equal to 1 and is 1.49 for English units. A Manning coefficient, which table 10.1 at the bottom of your screen defines, the hydraulic radius of the flow and the slope of the bed to some powers. If we want to get the volumetric flow rate, we just take the average flow velocity times the cross-sectional area, and that's what this is. And so those are the two expressions that we need. So for uniform flows, where the depth of flow upstream and downstream are the same, then we can get away with this characterization. It really is, and I'll just zip up to here quickly and come back, it really is exactly the same as using drag coefficients and friction factors in this part of the turbulent regime, where you get a single value of n, so n equals 0.1, n equals 0.01, depending on whether it's a glass channel, I don't know, I'm just choosing numbers, or a concrete channel, concrete line channel. And so that's really what these expressions are. They're just like the pipe flow equations, but for an open ditch. And where instead of being driven by upstream fluid pressures, it's being driven only by the gradient oriented in the direction of flow of the bed of the river. And so it just becomes a recipe to be able to use. So Manning coefficients don't depend on the fluids at all. They depend only on the characteristics of the channel. And so, you can think of all kinds of different classifications: natural channels, rivers with floodplains, where you're flowing through trees and brush, human-made channels as to what they are. And I guess the characteristics of them are that the Manning's number gets larger as it gets rougher. So this is smooth, rough, clean versus stony cobbles. And I guess I did use glass. Not very many channels would be glass, but this is certainly going from smooth to rough. And you see that the numbers go from small numbers to progressively larger numbers. So that's the deal. And so it's very easy to use. It requires, of course, that you know what your channel looks like. And so you need to be able to go into the field and to wade across the Allegheny River and to see how deep it is and how the section varies. But the ideas would be to be able to just get a value for the hydraulic radius, which we know, right? Done it already, which is area over perimeter. So this would be P, and didn't change the color, or it did. And this would be A. I think that's right, isn't it? Yeah. and then use a value for whatever the Manning's coefficient is for this channel. And then you have a depth. You need to know what the gradient of the channel is, how much it goes downhill over a given length. And you just need to plug and chug the numbers to be able to get it. And so I guess the subtleties of that are that you might have a channel, for instance, that would have a number of different components to it. So you could imagine that your channel could be a river that's overflowed its banks. And so the main river channel might have a different Manning's coefficient than the surrounding. I guess it would be the opposite here, right? You'd think that the channel would have the lowest number and the floodplain flowing through trees and brush would have a larger Manning's number, but it doesn't really matter. As the channel gets really wide compared to its depth, then the hydraulic radius, just by the way it reacts, if the hydraulic radius is the width times the depth divided by the width plus 2 times the depth, then as the width gets very large in comparison to the depth, then you're left with the value of the hydraulic radius being equal to the depth. I guess that makes sense, because the width cancels out both top and bottom. Y gets very large here, and 2 times y gets large here. If you have a compound channel, then you can solve this problem here by summing together the different flow conduits. So I guess this would be an analog to our series flow. So you have 3 pipes in parallel. The flow across those 3 pipes has to be Q1 plus Q2 plus Q3. The head drop across them has to be the same, because the upstream and the downstream, in this case driven by the gradient of the channel, have to be the same from upstream to downstream. So you can sum the individual flow rates on each one. So the flow rate for the total, in this particular case, would be equal to Q1 plus Q2 plus Q3. Q2 would be the flow rate physically into the page as an arrow. And the only thing you have to remember is that you need to use the appropriate Manning's coefficient for that channel, the appropriate K value. For SI units, this is always going to be equal to 1. We'll only do it in SI units. The cross-sectional area, which would be this area, and the appropriate radius, hydraulic radius. So the hydraulic radius for this, obviously, would be, I guess this is the important thing to remember, the perimeter of this one would be this length plus this length. It wouldn't include this part here. You're not going back up here. And the reason for that, obviously, is because as you go across this boundary, you have water going with water, and so it's not water stagnant and moving water on one side, but they're both going down together. So there is no drag along this between the water. So it makes sense that you only use the perimeter, which is the wetted perimeter of the solid, not the wetted perimeter of the interior. So I guess the hydraulic radius 1 would be equal to A1 over P1, right? So it'd be this area here, and this perimeter, which would only be these 2 legs, not this part here. So you see that. And if you can do that for one of these, then the perimeter for this one, I tried to change the color, but it didn't change. The perimeter P2 would be this part here, wetted only. I guess you can think of the wetted perimeter. And P3 would be this chart. So that's the only important thing to realize, I suppose. Some examples. I'm not going to do the examples because I think you can see those. There's always one of these questions on the test, and it's the recipe. It's pretty straightforward. But so you might want to look at these. And so we can also talk about the most efficient section. And so the most efficient section for a given gradient, so if the gradient's constant, the most efficient section will be one that has the highest hydraulic radius for the cross-sectional form. And so if you find a form or a cross-section which has the highest hydraulic radius, then by definition you have the highest flow rate for a given gradient, and therefore you have the most so-called most efficient section. So it turns out that the most efficient sections are, for a circular one, is if it's bank full to the top of the radius deep, so the half diameter deep. So instead of being only partly filling the section, this would not flow with as high a velocity as being full. The most efficient rectangular section is the depth equal to half the width, which is a little bit like a circular pipe, but it's just not rounded corners. A triangular distribution where this is a right angle in the bottom, 90 degrees. And the prismatic distribution where if it has angled sides, that the sides are angled at 60 degrees and that the length of this side at 60 degrees is equal to the width of the bottom. And of course, if you know that, you'd be able to calculate what this particular part would be just by these angles. So that's it. That's it. So the only thing that's important that comes out of what we've talked about today, not the derivations, but these two formula, the Manning formulas. And that is, you get the velocity, which is uniform across the system, because we assume it to be that case, and it's given by a Manning coefficient, a hydraulic radius, and the inclination of the channel. And if we want to get the volumetric flow, we just multiply it by the cross-sectional area, and you have the same formula. And there's an example that does similar things, and a composite example as well. So you can, I don't think we need to go through those. So that's it. So, questions? Any? No, pretty straightforward, isn't it? So that's kind of closes off what we've talked about in terms of uniform flows. So what we'll talk about the rest of the time is how we distinguish what's going on in more interesting flow cases. And so if we go back, for those of you who perhaps came in a trifle late, we'll talk about the rationale of how, when flow goes down from upstream to downstream, you could imagine yourself sitting on top of your kayak on this flow here. It's going very quickly downstream and quite placid over a small cross-sectional area. The cross-sectional flow area is much larger here. If we're not accumulating fluid here, which we aren't, because if you take a snapshot now and then you take a snapshot again, it looks exactly the same between upstream and downstream, then what is it that causes this thing to happen? Going from very fast across a very small cross-section to going much slower across a much bigger cross-section. And we'll find out that this index is indexed in terms of the Froude number. This number, which is the index of inertial forces to gravity forces. And it really comes down to the fact that if you're sending information downstream, that information has to travel at the speed of the wave, the celerity wave. And if flow is faster than that celerity wave, then the information can't get upstream to tell it exactly what it's doing. It sounds complicated, but we'll deal with it. So the wave speed of the surface wave in transmitting information about what's going on downstream to upstream is an important feature. It's a bit like a Mach cone around an aircraft which is going through the sound barrier. The energy tries to get away from the nose of the plane. It can only travel at the speed of sound in air, and if the plane is going faster than the speed of sound in air, physically that energy can't get away from the nose of the plane. And so that's why people worried in the days when you're looking at going through the sound barrier, what kind of forces were applied on flight structures, because the energy can't physically get away from the plane because the plane is going faster than the speed of sound, which would dissipate that earthquake away from the nose of the plane. And so these flows are a bit like that. So that's it.